So this video is going to explain why you can swing a bucket tied to a rope above your head and the water doesn't fall out. So first we're going to consider what is the free body diagram for this problem at the top of the cycle. And we're going to think about the forces on the water inside the glass or the bucket. And so we've got the normal force on the bucket from the glass, which is pointed down, and the force of gravity, which is also pointed down. And then we know that the net force in this case is going to be equal to our centripetal force, and that should be pointed down. Okay. And so we can write each of these as vectors. So on the left, we're going to sum up all of our forces. So we've got negative n. The negative sign is because it's directed down. Minus mg. Again, the negative sign is because it's directed down. Is equal to, and then the magnitude of the centripetal force we know is mv squared over r, and it's also directed down, so that's negative mv squared over r, where r is the length of this rope. Okay. Now we can multiply this entire equation by -1, and we will come to this, that n plus mg equals mv squared over r. Okay. All right. Now let's try putting some numbers in and use this to find what is the normal force on this glass. Okay. And if you're doing this video, watching it for the first time, I would suggest you pause the video here, give yourself a shot at doing the problem on your own before you watch my solution, and then I'll go ahead and post a solution for how we can set this up. So we're going to use our equation from our last video, n plus mg equals mv squared over r. And so then our normal force is going to be mv squared over r minus mg. We can plug in numbers here. So our normal force is 0.4 kilograms times 6 meters per second squared over the radius, just 0.6 meters. And then I've kind of run out of space for myself, but I'm going to subtract 0.4 kilograms times 9.8 meters per second squared. And when we plug those numbers in, we will get 20.1 newtons. Okay. Now, let's think about a different moment in time, which is on the bottom of our swing. Okay. Now, at this point, I'm going to ask a new question here, is what's the relationship between the normal force and the gravitational force? And does it change from at the top? Okay, so again, if you're watching this video at home, take a moment, pause it, pause the video, try to solve it before you look at my solution. Okay, so now, in order to solve this problem, we want to consider our free body diagram again. And this time here at the bottom, we're again going to draw our forces on the glass. So, on the water. And so the force on the water going down is mg. And then there's also a normal force pointed up. Those are our only two forces. And just like before, we know that our net force should be equal to our centripetal force. Okay. Remember, again, the centripetal force is not some magical extra thing. It's caused by the other forces already on the system. So here, our net force is equal to our centripetal force. Our centripetal force is always directed to the center of the circle, which in this case is up here. So our F net goes in this direction. Okay. Now, we know that we can write the sum of all of our forces equal to our net force. So in this case, our normal force is pointed up, so it's positive. Our gravitational force is pointed down, so it's negative, and that's equal to mv squared over r. Okay, now this tells us that our normal force must be greater than our force of gravity. Why? Because we know that the net force, we also could have looked at the picture rather than doing this mathematically, right? So you can either look at this mathematically and see that we can move the mg over to the other side of our equation. So then we have mv squared over r plus mg. This term is always positive, right? Mass is always positive. Radius is always positive. Our velocity is squared, so that's always positive. It's added to mg. So the normal force must be greater than mg. You could also have come over here to your picture and looked, remember that the net force needs to be positive, and then we just have the normal force and the gravitational force. For those to add up to something positive, then the normal force has to be greater than the gravitational force. Okay, this is just showing this in a diagram. All right, and so then we can use this same set of equations to solve for the normal force at this moment, okay? And again, pause this if you want to work it yourself. I'm going to go ahead and go through this fairly quickly because it's quite similar to the other one. So I just wrote down at the end of the last slide that our normal force was equal to mg plus mv squared over r. And that is going to give us 27.9 newtons. So this is greater than the one we found before, right? Remember, when the glass was at the top, we ended up subtracting and finding the difference between those. Here at the bottom, they end up added together. So we get a greater normal force at the bottom than at the top, just as we expect. Okay. All right. And that's the end of that video.